Today we start with lecture 10 of the course Artificial Intelligence. In the last class we introduced what you mean by constraint satisfaction problems, and we looked at how we cast such problems as search problems and solve them by depth first search with backtracking. Today we will explore some more efficient techniques for solving constraint satisfaction problems. The instructional objectives of today's class is as follows. In this class, the student will be introduced to more efficient search for constraint satisfaction problem. We will talk about the following strategies: forward checking, then we will look at constraint propagation algorithms like the AC3 algorithm, then we will briefly talk about intelligent backtracking or back jumping. On taking these topics, the student should be able to apply these techniques to constraint satisfaction problems. So before we start, let me try to briefly recapitulate the formulation that we did for constraint satisfaction problems in the previous class. So if you remember, the sort of constraint satisfaction problems we were looking at, we had a number of variables and each variable had a domain. So V1 is a variable and V1 has a domain. It can take a set of values. V2 is another variable. It can take some set of variables, some set of values. So we have different variables along with their domains. Our objective is to assign variables to values. And the value for a particular variable must come from its domain, and the constraints must be satisfied. So constraints, we especially looked at a most common type of constraint called binary constraints. Binary constraints involve a pair of variables. Suppose we can have a constraint saying that V1 and V2 cannot have the same value. This is one type of constraint. We can say that the constraint between the variables V2 and V3 is that the value of V3 must be greater than the value of V2. So we have a set of variables. Each variable has a domain. The variables must be assigned values from the domain such that the constraints are satisfied. So this is the general class of constraint satisfaction problems. Now, these constraint satisfaction problems can be cast as state space search problems, and we can do the search in the following manner. We pick up a variable. So this is the start when none of the variables are assigned any values. So V1 is not assigned a value, V2 is not assigned a value, V3 is not assigned a value, and so on. So this is the empty state when none of the variables are assigned any values. In the next step, we look at the assignment of different values to variable V1. Suppose variable V1 can take the values 1, 2, 4, 7. So we have 4 branches corresponding to all the possible values that V1 can take. In the next state, we have to pick up another variable. Let us say we pick up V2, and we have to look at all possible assignments of values to V2 that are consistent with the assignment that we have so far. For example, if V1 has the domain 1, 2, 4, 7, and V2 has the domain 2, 3, 4, then if V1 is already 1, V2 can be either 2 or 3 or 4. If V1 is 2, V2 can be either 3 or 4. We cannot have V2 equal to 2, because any further assignment after we have V1 equal to 2, V2 equal to 2 will not undo this constraint. So, if we have an assignment which is inconsistent, we should not proceed further in that direction. Next, suppose we have another variable V3 which has a domain, let us say 1 and 5, and we have the constraint that the value of V3 must be greater than the value of V2, then in this case V3 can only take the value of 5, in this case V3 again can only take the value of 5, and so on. So, in this way we can construct the search tree corresponding to the constraint satisfaction problem, and we note that a solution to the constraint satisfaction problem is a leaf in the search tree which corresponds to all variables being assigned to specific values that do not violate any constraints. So, all the leaves at level n, if there are n variables, all the leaves at level n are the different solutions to the search problem. And the strategy which is very appropriate for solving such search problems is depth first search. Whenever we find that a constraint is violated, we do backtracking. This backtracking is called chronological backtracking, because we backtrack to the previous choice point. So, depth first search with chronological backtracking is a very appropriate method for solving constraint satisfaction search problems. In the last class, we also discussed that we can try to make the search efficient by looking at a proper ordering, proper order in which we choose which is the next variable we select next for assignment. So, this is a heuristic which might, so if we take a proper order of the variables, we might end up in reaching the first solution much faster. And then once we pick a variable to assign values to, we will be considering in what order should we assign values to these variables. Then we will look at other questions like, can we detect inevitable failure earlier? So, in the general search problem, we said that whenever we see that a constraint is violated, we terminate the search at that point and then backtrack to the previous choice point. But it may be the case that future problems can be detected even earlier on, and today we will see some techniques to handle that. And then there is the question whether we can take advantage of the problem structure to further prune the search specific to a particular problem. Now, as we already discussed in the last class, one heuristic to choose the next variable is the minimum remaining value heuristic. In the minimum remaining value heuristic, the variable with the fewest remaining values is chosen next. What do you mean by variable with the fewest remaining values? You see, we said that every variable has a domain. Now, as a result, so when we have a partial search tree, some of the variables have been already assigned values, and as a result of these assignment of values, let us say to V2 and V3, the domain of V1 has become restricted, the domain of V4 has become restricted, domain of V5 has been restricted. So, we find out the size of the domains of the remaining variables, and we pick the variable for whom the remaining domain is smallest in size. The intuition behind this is that the variable which is most constrained, since in the constraint satisfaction solution to the constraint satisfaction problems, all variables have to be assigned values. The variable which is most constrained will have the fewest remaining values, so we need less of backtracking in order to consider the effect of that on the search. Next, once we have chosen a variable, we have to choose the order of value assignment. And here the heuristic is choose the least constraining value. You see, all variables have to be assigned value in the solution, but each variable has to be assigned only one value. So our intuition is choose a value which is most likely to take you to a solution. And so consider that value which constrains the domains of the remaining variables the least. That is the value that rules out the fewest values in the remaining variables. Now, we also discussed briefly that apart from the depth first search formulation that we are considering, we can propagate constraints earlier on. So, instead of considering variables one at a time, we look at the constraints early on to reduce the search space. And there are several ideas which people have formulated which gives rise to different algorithms for constraint satisfaction search. The simplest of these ideas is forward checking. So, what is forward checking? We keep track of the remaining legal values for the unassigned variables. So, when we assign values to a variable, we suitably constrain the domains of the remaining variables. And then if we detect that there is a variable which does not have any legal values left, then we can immediately terminate that path. Because along a path, finally we have to assign values to every variable along a correct solution path. So, if you find that there is a variable which does not have any legal values left, we will not be able to assign values to the variable. So, that search path is bound to fail. So, if we can detect this early on, we can terminate search at that point of the search tree. So, for example, this is an example of a graph coloring problem where we have 5 nodes and there are 3 colors, red, green and blue, and these are the links in the graph. So, corresponding to this problem, suppose we show how a constraint satisfaction search proceeds. So, initially suppose we pick the variable MH, node MH, we can paint it red, green or blue. If you paint MH red, then if you pick Kn next, Kn is a neighbor of MH, so Kn can be either green or blue. If we pick Kn equal to green and then we pick Ke next, Ke is a neighbor of both MH and Kn, so Ke has to be red, Ke is a neighbor of Kn, so it has to have a different color than Kn, so it can be either red or blue. So, this way we can construct the search tree and we can do depth first search. Now, if we do forward checking, let us see how we will proceed. Initially, we have 5 variables MH, Kn, Ke, Ep and Tn. Each of these variables can take each of the 3 values red, green and blue. When we set MH equal to red, Kn and Ep are neighbors of MH, so they can be either G or B, the others can be RGB. If we pick now Kn equal to green, then Ap, which is a neighbor, cannot be green, so it can only be blue. Ke and Tn can be either Rb or Rb, they are also neighbors of Kn. Then we pick Ke equal to red, as a result Ap and Tn can be only blue. Now, if we take Ap blue, we find that Tn the domain of Tn is empty because Tn is a neighbor of AP. So, we detect here that there is a problem with this assignment and we backtrack. So, this is what forward checking does. Now, you see that let us look back at the figure. You see, at the fourth step, we found that Ke and Tn have only blue left in their domains. Now, Ke has a legal value left, Tn has a legal value left, but we also know that there is a constraint between Ke and Tn. Ke and Tn cannot be of the same color. So, we notice here, sorry, we are talking about AP and Tn, they cannot be of the same color because they are neighbors. So, in this step we see that AP and Tn have only one legal value left. So, even though they are individually legal, together AP equal to blue and Tn equal to blue cannot happen. So, a smart algorithm might detect this early on and terminate search. So, this is a limitation of forward checking. Forward checking checks that every remaining variable has at least one legal value, but it does not explore further whether these values can be assigned to this variable subject to the constraints between these variables. So, forward checking detects some of the inconsistencies, but it does not detect all inconsistencies. For example, in the previous example, it does not detect that AP and Tn cannot be blue simultaneously. Now, let us look at another constraint graph on which we will run the next algorithms. So, in this graph, again this is a graph coloring problem. We have 6 nodes which we have numbered 1, 2, 3, 4, 5 and 6, and this is the connectivity information between the nodes. Each of the nodes can be colored red, green or blue, but 2 neighboring nodes cannot be assigned the same color. Now, if we do forward checking, let us see what happens. Suppose we first pick up 1 and we assign 1 to red. Now, if we assign 1 to red, 2 and 3 cannot be red. So, we reduce the domains of 2 and 3, they are blue or green. So, for each variable which is in constraint with 1, we eliminate the conflicting values from the domain. Now, next suppose we assign green to 4. Now, if we assign green to 4, 2, 3 and 6 cannot be green. So, we remove green from the domains of 2, 3 and 6. Okay. Now, 2 can be only blue, 3 can be blue, 6 can be red or blue. Next, we assign blue to 5, and as a result it affects the domains of 3 and 6. So, we remove blue from the domains of 3 and the domains of 6. Now, as a result we see that the domain of 3 becomes empty. So, this is impossible. So, we have to backtrack at this point. So, let us now look back and see what is the weakness of forward checking. You see, when we assigned 4 green, we saw that 2 and 3 have only one legal values left, which is blue, but these 2 legal values cannot be assigned together. So, we should have detected this problem early on. Forward checking does not detect this. So, this is not detected by forward checking. We should have backtracked at this step. Now, let us see what further improvements we can do. And so, there are several things that we could do. One is we could try to propagate the implications of the constraint on one variable onto the other variables. We propagate not just values, but constraints between these variables. So, this is the idea of constraint propagation that we will explore next. Secondly, what we will see after that we can backtrack intelligently, which we call conflict directed backtracking. So, we will save possible conflicts for a variable value when we assign that variable value, and we will back jump to that assignment which gave rise to this conflict. In chronological backtracking or normal depth first search, we backtrack to just the previous choice point. In back jumping, when we detect a constraint violation, we backtrack to that assignment which led to the conflict, which could have taken several decisions earlier. So, first let us explore constraint propagation. Now, arc consistency is a fast method for constraint propagation. So, this is how arc consistency works. Given the current domains of V1 and V2, the arc from V1 to V2 is consistent if for every value x of V1, there is some value y of V2 that is consistent with x. Okay. So, in forward checking, we just said that check if the domain of, if the remaining legal domain of V1 is empty or not. Here, we are not only checking whether the domain has a value, we are just checking whether for every value that is left in the domain, there is some value y in the domain of another variable, so that these two assignments of values are together consistent. That is what constraint propagation does. There are several constraint propagation algorithms. We will look at AC3 and some algorithms like that. Let us see an example of the same graph that we discussed earlier. We assign green to 4. After we assign green to 4, we check all the arcs from 4, 2, 3 and 6. First we check 2. So, when we check 4 equal to 2, we eliminate green from the domain of 2. Then, but we have to check back to later with the variables with which 2 has some constraint. Next, we check the constraint 4 to 3 and eliminate green from the domain of 3. After that, we check the constraint 4 to 6 and eliminate green from the domain of 6. Now, after we have finished checking the neighbors of 4, we go back to those variables whose domains have been changed to check if their current remaining values are consistent with the values of their neighbors. So, we now go back to 2 and check the neighbors of 2. First, we check 2 with 1, there is no violation, there is no problem. Then we check 2 with 3, and then we notice that if 2 is blue, 3 cannot be blue. So, we eliminate blue from 3. If we do that, the domain of 3 becomes empty, which cannot happen. So, we backtrack at this point. This is the arc consistency algorithm, and we can backtrack when we detect that there are variables which do not have domains which are consistent together because of the constraints between those variables. So, this is the idea of arc consistency. Whenever the domain of a variable is revised, the other arcs may need further revisions until no more inconsistencies remain. Okay. Now, one implementation of the arc consistency algorithm is the AC3 algorithm. The AC3 algorithm uses a queue to keep track of the arcs that need to be checked for consistency. Because as we said that when we assign 4 to blue, 4 to green, it is not enough that we change, that we check the domains of 2, 3 and 6 which is neighbors of 4, but if these domains did change, we have to check 2 with its neighbors and do this recursively until there is no further constraint propagation. So, AC3 does this constraint propagation, and in order to keep track of, so whenever the domain of a variable is reduced, according to this algorithm, you propagate the constraints to the neighbors of that variable. So, this is done recursively in the AC3 algorithm. Now, let us look at an implementation of the AC3 algorithm. So, we have a data structure of a queue. Now, initially the queue contains all the arcs of the graph. So, we have all the Vi, Vj that are in the graph, in the arcs, in the that are the edges of the graph, such that I not equal to j. Then while Q is not empty, we select one of the arcs from this Q, let us say that is Vk Vm, and we delete Vk Vm from Q. Then we check if revise Vk Vm is true. That is, when we delete this arc, we see if the domains get reduced. When we consider this constraint between Vk Vm, we check if the domains of these variables get reduced. If that is true, then, so as a result of assignment of Vm, if the domain of Vk gets changed, then we check, we find all the arcs in the graph of the form Vi Vk. That is, if Vi is a neighbor of Vk, then we have to check those constraints. So, we append to the queue all the arcs Vi Vk. If as a result of an assignment to Vm, the domain of Vk gets changed. Now, let us see what is the complexity of this algorithm AC3. Now, if we have a binary constraint satisfaction problems, then the constraints are only between a pair of variables. So, there are at most n square arcs in the constraint graph. You see, in the algorithm, every arc can be inserted at most d times if the domain of Vi has d values. So, when we are revising, when we are putting an arc involving a variable into the queue, we are only doing it when the domain of the variable is reduced. So, suppose initially the domain of a variable, let us say Vk, has d values. We consider this arc for revision only when this domain is getting reduced. So, corresponding to every Vk, the arc can be put into the queue at most d times. Now, checking the consistency of an arc can be done in order d square time, because we check it against all the arcs in the graph. So, the worst case time complexity of this algorithm is n square times d square, which is big O of n square d cube. So, O n square d cube is the worst case complexity of the AC3 algorithm. Now, so that is what constraint propagation is about. In constraint propagation, we, as a result of reduction in the domain of a variable, we look at the implications in terms of the constraints of the variables with other variables. And there are a set of algorithms which do constraint propagation. One of the well-known algorithms are AC3, which we discussed. Next, we will consider another technique which we mentioned as intelligent backtracking. We have already seen backtracking, which has a very important role in solving constraint satisfaction problems. So what you have in plain depth first search is chronological backtracking. When the branch of a search fails, we need to backtrack to the most recent choice point. This is called depth first search. In depth first search, we backtrack to a conflict point. So in depth first search, we backtrack to the previous choice point. But intelligent backtracking involves backtracking to the point where, because of which the conflict has arisen. So if suppose we have a search tree like this, and we have a constraint violation here, in chronological backtracking what we would do is, if there is a violation here, we will go back here and then go back here, which has a choice point. So we will go back to this node, which is the next choice point. But in chronological backtracking, if you find that this violation is because of an assignment here, we will backtrack directly to this place. This is called back jumping or conflict directed back jumping. So in chronological backtracking, consistency check is performed in the order in which the variables were instantiated. If consistency check fails, we try the next value of the current variable. If the current variable has no more values, we backtrack to the most recent variable which has a choice left. This is what is done in normal depth first search. Back jumping is also a type of backtracking, but it is more efficient when there is no consistent instantiation to be found for the current variable. And in this case, we go to the deepest variable which was constraint checked against the current variable. So when we find that the current variable is inconsistent and has no possible instantiation left, instead of backtracking only to the previous choice point, we find out what is the last variable which constrained the current variable. Do you see? The current variable has no legal values left. In order that the current variable does get some legal value, some constraint which participated with the current variable has to be changed. So we find the deepest node in the path from the current variable to the root where a variable was assigned a value and that constrained the domain of the current variable. We have to find that. So that is what intelligent backtracking does. Back jumping reverts to the deepest variable which was checked against the current variable and which introduced the constraints. Now let us look at this example. So we have here the 6 queens problem, and we have put queen 1 in row 2, queen 2 in row 5, queen 3 in row 3, and queen 6 and queen 4 in row 6. Now after that we have put queen 5 in row 4. Now we see that after we have placed these 4 queens, none of the other this last queen cannot be placed in any of the rows. So, we do not really need, so when we cannot put queen 5, we really do not need to look at any further assignment to the value of queen 5. Okay. So, with this, let us wrap up today's lecture. So, in today's lecture, we have looked at some efficient constraint satisfaction problems. We have revised forward checking, then we have looked at constraint propagation, for which we looked at arc consistency algorithms. And then we looked at back jumping. And what is the idea behind these algorithms? In forward checking, when we assign values to some of the variables, we look forward and then we update the domains of the remaining variables. And in forward checking, we just check whether the domain of any of the remaining variables become empty. If they do become empty, then we terminate search at that point. In constraint propagation, in the general constraint satisfaction class of problems, what we do is that we not only propagate the constraints to restrict the domains of the unassigned variables, but we also do a consistency check on those variables which have constraints between them. That is, we check whether every variable whose domain gets affected, whether it has a legal value for a legal value of its neighbor with which it has some constraints. AC3 is a constraint propagation algorithm which does this recursively. Whenever it reduces the domain of a variable, it takes up those variables and looks at its constraints with its neighbors. If there are constraints with its neighbors which reduces the domains of the neighbors, then again it checks those with their neighbors and so on. So, AC3 is actually quite AC3 is a quite efficient algorithm, and it is able to detect constraints earlier. Now, here you must note that you see, as you make your constraint checking algorithms very intelligent, you are reducing your search, reducing the number of nodes in the constraint satisfaction tree that you are going to search, but you are spending more time at every step. So, you have to select a right trade-off about whether these intelligent processing does give you benefit. These take up time, whether the benefit that you get in terms of reduced search space, if they warrant that sort of benefit. Finally, we looked at back jumping. What back jumping does is that when in your search tree some constraint is discovered, some conflict is discovered, that is, the domain of this variable has become empty. In back jumping, we find what is the earliest variable which had been checked with this variable and which introduced some constraint. Now, we must undo those effects in order to get out of this situation. So, instead of going to the next to the most recent choice point, we jump to a conflict point. Now, we look at the questions for this lecture. The first question: apply the different constraint satisfaction algorithms that we discussed in today's class on the 5 quints problem. In each case, you should find out the number of nodes that are expanded. So, first you will try ordinary depth first search. Second, you will try variable ordering heuristic along with ordinary depth first search. In the third instance, you try forward checking. Fourth instance, you work out AC3, and finally, you work with back jumping. So, we have come to an end of today's lecture. Let us look back briefly at the questions that we set for lecture 9. So, if you remember, the first question asked you to do the classroom scheduling, to look at the classroom scheduling problem and formulate it as a constraint satisfaction problem. So, let us briefly look at the classroom scheduling problem. So, we have a number of classrooms. Suppose CL1, CL2, CL3 are the classrooms, and we have some time slots. Let T1, T2, T3, T4 be the time slots, and we have some teachers. So, let P1, P2, P3, P4 etc. be the teachers. Now, this teacher, for each teacher we have a set of classes which the teacher should be able to teach. So, let us say P1 should be able to teach CL1 and CL2. P2 should be able to teach, let us say, CL2 and CL3. P3 should be able to teach CL4. P4 should be able to teach CL5 and CL1. So, we have a set of teachers, and each teacher should be able to teach a set of classes. Now, we have to assign classes to classrooms and time slots. So, we have also a set of, we have to assign courses. So, we have a set of courses. Now, this is a constraint, this is a problem which involves a large number of variables of different types. Now, let us look at the basic types of constraints which are involved. Now, if a teacher has to teach both CL1 and CL2, which means that, not CL, the course 1 and course 2, then it means that course 1 and course 2 must be in different time slots. If a teacher is teaching C1 and C5, it means C1 and C5 must be in different time slots. Okay. Now, each classroom at a slot can have only one class. This is something that you have to follow. And if a teacher is teaching 2 classes, those 2 classes cannot be at the same time slot. Now, what we have to do is we have to assign classes to classrooms and time slots. Okay. So, we can start with picking, let us say, class C1 and assigning it to classroom 1 time slot T1. Now, if C2 and C5 cannot have the same time slot, C2 domain will not have T2, will not have this time slot T1, and C3's domain will also not have, sorry, C5's domain will also not have T1. Okay. And then, so when we consider the next instantiation, when we look at C2, we have to look at the choices for C2 in time slots other than T1. When we look at C3, if we after C1 we look at C3, C3 can be in time slot T1, but in time slot T1 it cannot be in a classroom CL1. So, any two courses cannot share the same room and slot. So, both room and slot cannot be the same for two courses, and two courses that can be taught by the same professor cannot share a time slot. So, based on this constraints, we have to do the assignment of values. So, this you can work out for a small set of values. The second problem that we set was a cryptarithmetic problem. Specifically, we were asked to work out the values of the different letters for this cryptarithmetic problem. So, I will discuss briefly how you go about the solution to this problem. And you can learn sometimes for these problems, if you are working out manually, you can use certain heuristics from your knowledge. So, you see the value of m in this case cannot be more than 1, the value of m. So, even if s and m have the highest, if have values, this can be at most 1. So, this is not 0, because if this value is 0, we would not be putting this here. So, this is very easy to see that m is equal to 1. So, what we can do is, we can simplify this problem by putting 1 in this position. Oops. Now, we have some other variables left. What are the variables that we have? The variables are D, E, Y, N, R, O and S. So, we have 7 variables in this problem. So, let us say we first pick up D. Now, what are the values that D can take? D can be 1 or 2 or 3 or 4 or 5 or 6 or 7 or 8 or 9 or 0. So, we try the different values of D. Okay. So, there are many possible values of D. So, we will try all possible values of D. Now, let us say first we try D equal to 1. Now, if D equal to 1, we have to try the different values of E. Now, suppose we first try the value E equal to 1. Now, if E equal to 1, then Y has to be equal to 2. If D is 1 and E is 1, Y is 2. So, Y is fixed. Okay. And if Y is fixed, we have to look at, so here we have E is 1, this E is 1, this is the values that we have assigned, and Y has become 2. Okay. Now we have to choose n and r so that we have a 1 here. So suppose, we choose the different possible values of n. Suppose we first choose n equal to 1. If n is equal to 1, then r has to be 0 to satisfy this constraint. Okay. So we have this assignment, and then E is 1 along this path, and we do not know the value of O, and n is 1. So E is 1, O is not known, n is 1, so O must be equal to 0. Okay. So here we have O equal to 0 and we have this is 1, so S must be equal to 9. So a solution to this problem is S is equal to 9, E is equal to 1, N is equal to 1 and D is equal to 1. M is 1, O is 0, R is 0, E is 1 and M is 1, O is 0, N is 1, E is 1 and Y is 2, and you can verify whether this is correct. 1 plus 1 is 2, 1 plus 0 is 1, 1 plus 0 is 1, 9 plus 1 is 10. So this is a solution to the cryptarithmetic problem cent plus more equal to money. And we have solved this problem by simple depth first search, and in this case this is a simple problem, many solutions, so we could get this problem by only exploring one path very easily. Okay. So we will stop here today. In the next class we will first briefly discuss the answers to today's problem, and we will start on the next topic, which is on machine learning. Thank you very much.